Okay, so we're looking today at more than two independent random variables. Last lesson, it was combining two independent random variables. Today, we're just looking at more than two. So basically, you just need to again know the rules here. So if you had expectation last lesson of x1 plus x2, you could just do the expectation of x1 plus the expectation of x2. Basically, you just need to know that if it keeps going, you can just keep going with your expectation, okay? So if you've got like 4 expectations, you can just add up all the expectations, okay? Depending on the plus minus situation. You know, sometimes you've got 2 expectations that you add together and 1 that you take away. That's fine. Okay, plus or minus, okay? So, yeah, so if you've got 2 expectations and a third expectation that you would subtract, just add the 2 and take the third one away. That simple, okay? With variance, it is different in the same way that it was different in the last lesson. If you've got multiple independent random variables that go on forever, and you've got adding and subtracting of those variables, for the variance, it's just always adding, okay? Even if you've got 2 that are added and 1 that's taken away, it's always going to be added, okay? Is that all right? Make sense? Yeah. Well, it kind of makes sense from the concept that if you were to add 2 expectations anyway as a combined, and then you introduce a third one which you're going to combine, it's got the same result anyway because you've already combined 2 for an expectation. So that in itself is a new expectation, and bringing in a third one just has the same laws, okay? The same rules, okay? What's that? If x1, x2, xn is a set of normally distributed variables, then the distribution is also normal. Okay, so I suppose that's kind of important. I think that's something that you look at maybe a bit more later on, but maybe now. No, actually, no, it's now. Okay. So yeah, it's the last thing on there. If x1, x2, all the way to x to the n is normally distributed, is a set of normally distributed variables. I can't write today. Then the combined distribution, then the distribution x1 plus or minus x2 plus or minus ... plus or minus xn is also normal, okay? That's really important because it'll allow us to then apply our normal distribution stuff so we can find the probabilities of things. So if you've got 2 distributions that you're then combining, you can then find the probability of a certain event happening. Okay, that's why we care about combining expectations and variances, so that we can also calculate probabilities. So if we look at the first example here, it says the mass of a suitcase at an airport is modelled as being normally distributed with mean 15 kilograms, standard deviation 3 kilograms. Find the probability that a random set of 10 suitcases weighs more than 154 kilograms. Okay? 10 suitcases. Am I multiplying by 10 here? Is it, am I using the rules of today, as in the adding and subtracting things, or is it the rules of our first lesson, where our expectation is going to be times by 10 and our variance is going to be times by 10 squared? Am I using ex1 plus x minus 2? This is the question. Am I using ax, which is a ex, and var ax, which is a squared var x? And how do we know when to use which one? Is it a multiplication or is it an addition? Does it matter? It does matter, hence why there's two different formulas. Okay? Right? So it definitely matters which one we are using. Okay? But if it's 10 lots of the same thing, is it a multiplication or is it an addition? Hands up if you think it's multiplication. Hands up if you think it's addition. Hands up if you don't know. There must be everyone else's hands. There's like 4 people who put their hands up then. Right, so this is really important. This is part of what we're going to be looking at today, is when are you multiplying and when are you adding? Okay? Each one of those suitcases is its own identity. Okay? So because each suitcase is its own identity, you are doing an addition. Okay? It's not this exact same suitcase replicated to 10 times. That's the key difference. So every time you have the suitcase, it's a new suitcase, so you've got to add it and not consider it as a multiplication. So for this one, you're technically going to be adding it up 10 times. However, you know the value for your expectation when you're adding it up 10 times is just going to be 10 times that value. Okay? The only real difference, other than the expectation, is for the variance. The variance is the only place where that really matters, because 10 var x is very different to 100 var x. Okay? Which is the difference between timesing it by 10 or timesing it by 10 squared, which would be the multiplicative approach to it. So for the suitcase question, it wants you to first find the probability that a random sample of 10 suitcases weighs more than 154 kilograms. So your expectation of one of the values would have been 15, but we're going to add up all of it all the way up to x10. But every expectation is going to be equal here. So it's just going to be 15 added to itself 10 times. So it's just going to be 10 times 15, which is 150 kg. We good with that? Yeah. Okay, for variance, same process. Our variance is going to be x1 plus x2 plus all the way up to x10, which is going to be 9 added to itself 10 times. So it's going to be 10 times 9. So that is 90 kilograms. Okay? So our normal distribution, because it says that originally it's normally distributed 59, you can say a combined distribution of x, which I'm going to call xt, has a normal distribution which is 150, 90. Okay? Cool? Okay with the notation there? Yeah, mean variance, good. Right. Then it's just about calculating based upon normal distribution. I suppose they've used t rather than xt, it doesn't really matter. So we're looking at the distribution where our mean is 150. It's wanting to know 154 and greater than. So we want that region there. So we're going to do 154 for our z value minus 150 over root 90. Okay. And then 1 minus that eventually. But that gives us a z value of 0.422. Our phi z is going to be 0.6653 based upon the table. So our probability x is greater than or equal to 154 is going to be 1 minus 0.6653, which is 0.3365. Oh, sorry, got the numbers wrong way around there. 35. Okay, cool. Is that all right? Yeah. Basically, it's just identifying that the combined distribution, you're adding it, and then it's just your normal distribution stuff. Your normal distribution. Normal. Okay. And you will look at some slightly different normal distribution stuff later on, but that's for a while. Okay. So, yeah, it talks about, on page 270, linear combinations of 2 or more independent random variables. Okay. So linear combinations is where you've got your multiplication. But if you've got a linear combination of 2 or more independent, for instance, you've got one thing that's multiplied and you've got another thing that's multiplied, but you're adding those two things together, the rules apply of treat each one as the linear combination, so the A expectation and the A squared var x, okay? But then you can add those two different distributions together. So on 270 at the bottom it goes over that. So you've got expectation AX plus BY is equal to A expectation X plus B expectation Y. Okay? So expectation of the Y value. Does that make sense? If I also threw in like a plus or minus n, you could also throw in a plus or minus n there, but you don't tend to have that occurring. That's just more of the theoretical stuff that we did in the first exercise, less so in the practical stuff. But you could always have a look at shifting as well. But remember, the shift to the expectation effects are shifting the exact same way. Everything gets shifted by the same value. A shift in the variance does not affect the shift. Shift in variance does not affect the variance. Okay. The other thing is the var ax, plus or minus. Var ax plus or minus by is equal to a squared var x plus b squared var y. Okay. Always plus with variance, as we've done many a time now. Okay. So there's a question on 271. I'm not going to actually do this one mathematically on here. We're just going to look at it in the book, and I'll talk about it. It says, in a workshop, joiners cut out rectangular sheets of laminated board of length L centimetres and width W centimetres to be made into work surfaces. Both L and W may be taken to be normally distributed with standard deviation 1.5. The mean of L is 150 and W is 60, and the lengths L and W are independent. Both of the short sides and one of the long sides have to be covered by a protective strip. The other long side is to lie against a wall, so does not need protection. What is the probability that a protecting strip 275 centimetres long will be too short for a randomly selected work surface? Okay. First question is, are the widths the exact same? Instance. In this question, they have set it up so that that is the case. Both widths are the exact same instance. I would argue that actually the widths would be independent of each other, because if you ever actually cut a shelf, those widths on the either end are very rarely going to be exactly the same width. Okay? So it's a bit of I don't like it as a question, but they've set it up so that the widths are exactly the same. They've defined each width as having the exact same variable, W. Okay? It's not W1 and W2, it's just W. So when we consider our widths here, it's multiplicative. Okay? So when we do the total expectation, you're doing the length plus 2 lots of the width. So that's equal to the expectation of length plus 2 lots of the expectation of the width, which you'd be able to work out normally is 270. The big difference is for the variance, because we're considering it as multiplicative, we're now going to do 2 squared times our variance rather than just 2 lots of our variance. Okay? And this is where most people will drop marks in tests with these questions, is not being able to decide, is it multiplicative or is it not multiplicative? Because they've set it up where width is both W on both sides, it's multiplicative. Okay? So when we do our variance, we did 1.5 squared because they gave us a standard deviation, plus 2 squared lots of 1.5 squared because the standard deviation for our width and length were exactly the same. Once you've got your combined variance, normal distribution like you've done before. Okay? And it talks about it down at the bottom. Note, you've got to distinguish. Is it 2W or W1 plus W2? So be real careful in the question which they've defined.